Just starting. There we go. Of course, now my thing is gone. All right. Hello and welcome to Apropos, a conversation between Clojure programmers that you can join in live on YouTube. We're going to discuss a few Clojure news items and share our opinions on them. Then we'll jump into a REPL and code some exercises or do some demos. Very exciting part of the show. If you're joining us live, please feel free to comment in the chat. And we'll try to address questions. We usually do shout outs to people that we like, if they have good comments. So let me introduce our panel. Today we have Mia.
Hi.
We have Mike.
Hello.
Also Ray.
Hey.
Last but not least, I am Eric. And we also have 18 people with us on the YouTube live thing. Hello, everybody out there. So we have a nice topic today. We're continuing our code quality talk. This time we're talking more about testability. Ray, since this is your topic, would you like to start it off?
Yeah, I mean, it's obviously, like you said, it's a general topic. The thing I was thinking about was how do you make code testable in general, and then what does Clojure do to help? And I was really thinking about the fact that, essentially, if you're using a functional programming model, then you're more conscious of the fact that your functions should take some inputs and give some outputs, and ideally without making any kind of side effecting thing on the way as part of doing that. So as a basis for testability, that already seems pretty awesome for me. If your goal is to write those kind of functions and then compose those functions, in theory, you should have quite a nice pure system. So, I think obviously in the real world, when we write our systems, we're sending out emails or we're taking input from a user or we're putting information to logs. So, there are inevitably some side effects, some side effecty things. So the question really is like, okay, how do you account for that? What are the strategies for, assuming we all accept that's the case, and there are some good benefits in being on the Clojure world. What kind of tools does Clojure have to help us there? So I was thinking, first of all, just if we want to get an agreement across the board that the pure function stuff is the way to go for testability. Does anyone else have any thoughts on that?
Go ahead. Right.
No, that's why I started programming in Clojure, was frustration with testing in Java. Go ahead, Eric.
Yeah, I was going to say that my experience in doing testing in object-oriented languages or other mutable languages, I always tend toward functional. Like the tests push me in that direction because it just is the natural result of testing. It's like I don't want to have to launch rockets to see if this code is going to work. Let me make my code, make the plan for the rocket launch, and I'll just test that. So that's the functional approach anyway.
So even if you don't have like things that you need to mock out, let's just say you had like a simple object, right? And you're testing that thing and you mutate some field or two in it or some state, then you get into that pattern where you have to, write your test where even one that's not even mocked, just like, let's say you had a object that is itself mutable, and you have methods on it like setters that don't return anything, right? To test those, you have to call the setter and then the getter, Right. Now that's kind of silly to test those, but you know what I mean? You have to like mutate the thing and then you have to make an assertion about its post condition, I guess. And
well, then if you don't test that, like it seems silly to test those, but because you've got mutations happening, like the result could just be completely different because you changed something upstream. So
right, and you're only capturing the individual operations. You're not capturing like a stream of operations. Like it could be that there's a contract that you shouldn't call this after you set, or you have to set this first before you call that. And like, so then you have all these like pairwise interactions and
combinatoric explosion.
Yes. And the complexity of your object becomes clear. And so that, you know, to me, that is like one of the benefits of doing something like TDD, where you're actually being forced to test it, and you realize just how complicated your code is. And so that's what drives you to the functional side. It's just like, oh, I'm just going to simplify this. I won't have any mutation, because like you haven't even tested what happens with multiple threads and, you know, different things, setting things at the same time. And scary.
So you mentioned TDD there, and I've got to say, I mean, I was kind of very attracted to TDD when I was in the Java world and the mutable world, but I'm a bit less drawn to it now that I'm in Clojure. I get it, but I never use it. I tend to write tests after I've done things in the REPL that, you know, proven out something, and then I tend to write tests as a kind of something that will just prove to other people, if you like, that something works in the CI system. I don't know if that's what other people do as well.
Yeah, if you test every last little thing you're about to write, that gets to be tedious, right? It's nice to just kind of race ahead and flesh out some functionality, and then once you get it a little more solidified, then write some tests around that. That's what I like to do.
Do you do TDD, Mia?
I mean, it depends on what we're doing. So I usually start with like the basic behaviors that I expect out of whatever I'm writing, and then do the details in the REPL as I'm working, and then run the test at the end.
I tend to use TDD for very specific things where it's like very intricate. Like there's like, I know I'm going to have a big cond, you know, that's got like 17 cases in it. Like I want to test that, right? Like if I'm writing an interpreter, like I want to know, like, okay, if I pass it a number, I'm going to get a number back. If I pass it +1, it's going to give me, you know, it's going to work. It's going to give me the right answer. Because it's intricate, and it's like a recursive thing, and it's, you know, but typically I don't do that. When I want to figure out, like, I use TDD in the object-oriented world too, and I felt like a lot of it was just because you basically just have to get the steps in the right order. And so that you're just testing that, you know, every step is happening. And in Clojure, that's much less the case, that's what you're testing. That's where the challenge is. The challenge is more like, you know, I'm transforming this map in some like intricate way, like it's hard to keep it in my head, like what all the steps are. But then I just work at that at the REPL and add steps until it's doing what I want. And then I just put that code in a function. I don't consider that TDD.
So what about the more tricky parts then, like where, because there's sort of side affecting things, like where you're affecting the outside world, and there's this co-effect thing where the outside world is affecting you. Or, you know, so a classic example of that is time, where, you know, somehow, you know, you're using a date stamp or a time stamp or something like that in your function, or you're emitting a random number, you know, which is normally based on some kind of time thing. What do you guys do with that stuff?
Make it more functional, pass in the time, pass in the timestamp.
I try to avoid that at all costs now.
Yeah,
Almost just don't test those kind of things. Yeah.
It's also a good idea.
Never test.
Tests are good.
It's horrible. It's too hard. Forget it. You know, that's not what you meant, is it, Mike? But you know.
Well, I like to factor out the functional bits and test those, and you know, if there's stuff that you have to mock, then I'm more hesitant to go and do that part. You know.
Yeah, I just feel like that whole thing, it just shows like how complex the programming model is. You have to have a complex testing model to make it work.
We use Spec a lot for this kind of thing. Because most of our programming is passing messages into and out of Kafka. So for us, what we're looking for is, does the data have this specific shape? Mm-hmm. And with a well-defined spec, you can control a lot of, like, you can test a lot of that output very simply by just asking. You don't even have to examine the data that comes out. You just say, does the data that's coming out match with the spec?
Right.
So I'm curious, Mia, if you have specs, and let's say you write some generative tests or you have it produce them for you, the big question in my mind is, let's say those are expensive to run too, like you maybe run 100,000 to try to find some bug. What do you ultimately take any of that stuff and put them into the traditional unit test frameworks?
So we don't use generative tests well, that's not true. We do have some generative tests in our unit test, but for the most part, we reserve generative testing for integration tests and system tests. So things that are run deliberately at the end of everything. We do generate, data to test in unit tests, but it's usually only generate a message based on the spec and associate these values to it. So most of the really time-consuming stuff is only run once or twice in the process.
That's when you get into the generative testing stuff, that's where I start to actually feel like something is actually finding bugs, because it's finding weird corner cases that I didn't think about. Whereas the traditional example-based tests, it's good to write those down to prevent future regressions, but it's not like finding bugs in the code you're writing.
You have this idea of code coverage, which is that every line of your code was actually tested in some test, but it's not testing that whole multiplicative effect of different branches. It's only each branch was run once, not I don't know. You see what I'm saying? That there's this other complex thing that's not getting captured by coverage.
So I'm becoming a big fan of generative tests because it actually feels like it has value, and that it actually finds bugs in my code. I forgot to handle this weird case, an empty string or something, And
we love them. We love Spec. We rely really heavily on Spec here. Just
it leads to a lot of sanity, right? I mean, it's
yeah. It's one of probably the biggest thing that's been catching us is the difference between pos int and nat int.
Okay.
We have a lot of things that aren't actually allowed to be 0, and if you just use an int, it'll generate 0. So we had to figure out which ones don't do that. But that's a corner case that we wouldn't have noticed otherwise.
Yeah, and that's one of the cool things about generative testing is that your understanding of the problem is also being tested in a way that in unit tests don't.
Right.
It just doesn't happen in unit tests where you're like, maybe it shouldn't work that way. Maybe let's go back to the docs and see what it's supposed to be doing. You never do that.
Because you're sympathetic when you're writing your unit tests, even whether you like it or not, you're sympathetic to what it should behave like. But Spec doesn't give a shit. It's the honey badger of testing. It's just whatever.
Exactly.
So I'm just going to throw whatever I think at you.
What I'd like is I think Stuart Holloway mentioned this idea is let's say you have some cool generative tests and you run them and they're expensive, but it tests the crap out of your function. You'd like to take a snapshot or a signature to say this thing has been proven to have passed this test, so you don't have to run it again. But then if you change some function that function depends on, it's you need the transitive closure of everything.
You need a hat. So there's a language called Unison, and what it does is every time you write a function, it hashes the code. So there's an algorithm that recursively takes the hashes of everything you call, right? And everything that function calls and combines them into a new hash. And so if anything in the tree changes, everything up the tree has a new hash. Okay. And so that lets you identify exactly what
you tested. Yeah.
Yes, what you tested and what has changed and what needs to be retested.
They needed to build that in the spec then, because
that'd be
awesome.
Wow.
Yeah.
That'd be
Because
really
then you could
cool.
say like you could run the test and they could say, oh, I've got it cached that I already, I tested this and the hash stayed the same. I don't need to run the test again.
Right, especially
But
since like you might be better off using those CPU resources somewhere else. Because, like I feel like it kind of breaks the CI as a service model where like some computer in the cloud is going to run your tests for you, and like if your tests take less than a second, like they can shard out that computer to like hundreds of customers. But when you have basically unlimited tests that you can run and it could take unlimited time, like in theory you should just be running tests all the time.
Yeah.
Because
like if you have extra cores on your box, just
yeah, or in the cloud, what it's like a $5 AWS box could just be running generative tests all the time on your code. Right.
But it's like a choice, like how many of which tests do you run? Or like you get something like you always have to write generators, or you don't always have to, but quite often you have to write generators that are efficient, right? Otherwise you get a bunch of crap data that.
And I think that this goes to testability also. Like in my experience, if you try to just say, well, this is the like giant data structure that we're going to be passing around and we want to generate examples of this shape, you get to the same problem that you have with unit tests where you're trying to test something that's not very testable. And to me, like what you really want is small specs, right? You want combining forms for those shapes. And the generative testing actually pushes you in that direction because it's property-based testing. And so you have these properties like this operation is commutative, or this operation is reversible, and here's its inverse, right? And those kinds of properties are perfect for property-based testing. I guess that's why they gave it that name. I want to mention something I see in the chat. Alex Miller says that they have an implementation of this hashing idea. That uses Spec.
Yeah, but it says it's in 1.23 or something.
Yeah. Well,
that's very cool.
We got to get that over the line, Alex. So, that's what we got to do.
So with that,
go ahead. Sorry, go on, Mike. Yeah.
Well, so I'm still stuck. Like, what do you actually do? There doesn't seem to be a recommendation beyond running your generative tests in your REPL or something like that. Like, there's no thing in the tools that Cognitect offers to hook it into Clojure test.
Yeah,
you have to roll your own, right?
No. There's a runner that is like a def test, like Enclosure.test.
There's a def spec that.
Yeah, but not the spec. I'm talking about just regular test check.
Okay.
There's it's a macro that does that for you. It simultaneously defines a Clojure test and a property.
Yeah, so I've used that one. I think I know what you're talking about. It's called def spec, I think. And it'll basically.
Oh, that's right. You're right.
Yeah, so I've used that, and that's like the normal, like you write a generative test. And it kind of hooks into your test framework, and it'll run in CI.
Right.
And I've like resorted to, let's say the question is like, what if you wanted to hook in your spec-based test into that? You can,
Right, because you can get the generator from a spec.
Yeah.
Yeah.
But I wonder if that's even like the best approach. Like, I like this hashing thing where you run it yourself on your box and you're like, okay, this is good to go. Hash it. I'm done. No one ever needs to run this again because it's a pure function, or, you've proved that it's passed these tests. And
once a test passes, never run it again.
Like if it's a deterministic thing, why spend more CPUs on that?
Yeah.
You've done it.
It's true.
Like Eric says, if something that calls it has changed, then fair enough. If you can find those like dependency networks, if something in that Merkle tree has changed, then bam, you should run it again. But this is where all this kind of like Git is becoming like that thinking of everything being, dependency tracked, and it's becoming a very powerful concept. But I remember, didn't Rich do something a few years ago called Codec, I think it was called Codec, something like that, which was taking the Clojure code and saying, Git does differences at the kind of line level, which is fine, but actually it would be quite interesting to do for differences at the function level, and the definition level. And I think he did something by basically putting the code into the atomic and then doing, more interesting kind of queries on it as the code evolved. But again, it's like one of these, I think it was like probably some spike that he did and nothing really came of it, which was a bit of a shame because that would have been quite nice to have something like that in a language. And maybe that's what this thing that Alex is doing.
Yeah, maybe they revived it. Yeah.
Yeah.
Back in the day when I was a grad student, I did a testing. I wrote a paper on how to test, like looking at the branches that have changed when you make a commit and there are some branches that change. And so what tests do you have to rerun? Because some software has tons of tests and they're expensive to run. And so you don't want to have to run everything every time.
Yeah, like you have a gigantic code base, but you only changed one little corner over here.
Exactly.
And that only affects a certain subset of the functionality. Yeah.
Exactly.
Yeah, I think that we're doing something in Circle with that, where we're only running if something's changed. So that's actually cut down our build times quite a bit because we run Circle every time we try and build. And it used to take half an hour because we would test the same thing over and over again. Now it checks and sees which code has changed, and it takes 5 minutes.
So is your code base like partitioned in a way where you can run subsets of tests, or?
Yeah, we have like a whole set of Circle test runners. So we only have this done on Circle right now. We're using Circle's, like I think it's 2.0. They have functionality that allows this.
That's cool.
Yeah.
What's the difference between what Circle does and what you can do with standard Clojure tooling?
That I don't know. I was not one of the ones who was configuring this.
Oh, okay. Homework, man.
I've been like, I won't say I've been deliberately not learning it, but like once you learn it, then you're one of the Circle people, and then anytime something breaks.
Oh yeah.
No, I always kind of find it a little bit. I'm always a little bit wary of things that only a certain CI runner can do or run. I mean, I think of CI as something which is just a total, largely a commodity where you can just. They might have some affordances that are interesting, but it should just run your tests in the same way as you run them locally.
Should just run batch.
Exactly, yeah. And the only time you might want to like have differentiate, like I know that Circle has this ability to do like SSH into a failing machine and stuff like this. Those are quite nice affordances, so you can go in and find out something interesting. But otherwise, why? Why have these features in the CI environment that you don't have locally?
I guess because it allows you to specialize. Like if the CI environment is only specializing in test, right? It's just testing the code. You're not writing it and testing it. So in terms of what they can work on, what they can develop, they're going to be developing more stuff around being able to test things. Whereas if you're developing an all-purpose library, you're focusing on other things as well. It would be nice to have these things in everything.
Yeah, maybe that. I mean, I looking at the way that I used CI in the past is like for a Docker support where you have like 3 or 4 Docker containers starting up, then you say, okay, now start running the tests from beginning to end. But again, you can do that locally. It just so happens.
You can do that with Docker Compose.
Exactly. Yeah.
Has anyone used property-based testing, like in Anger?
I have a little bit.
What'd you use it for?
Just testing pure functions to find,
corner cases.
Like I would do like, does this thing have a inverse gets you back to the original thing? And you can find weird things that way.
Have you tested anything that wasn't functional with it?
Oh,
that's where it gets fun.
Okay.
I actually gave a talk on this, but I did I was writing
Was your database
cross
thing?
Yeah, it was like a key value store. It's cross-browser plugin, like Chrome extension, Safari extension, everything. And each one had its own API for their key value store. And so I wrote property-based tests that would make sure that they all, like my stuff was working in all three of them, so I could wrap up the differences between them. And it's pretty fun because you have to like model what did they do, like how should they be acting, and comparing that to what actually happens. It's pretty fun. And
Good.
John Hughes and I can't remember his name now. Guy working with him who was at the Conj a few years ago gave a talk on using it to test Dropbox.
Okay. Yeah.
And they had a whole setup where they were doing property-based testing on Dropbox to see how it synced the files.
And those might run a little bit slower, but you still get the shrinking in the end. And
yes,
yeah,
it was definitely slower.
Yeah,
it was like, you have to wait for it to sync, and you have to guess that it's done syncing. They had, this is all the like the stuff you have to do when you're testing a black box system. Is like model how it works, and you're evolving your test suite as you learn like what it does. So you're evolving your understanding of the system and your ability to test it at the same time.
Alex Miller pointed out that was Benjamin Pierce.
Thank you, Alex.
The other story that I heard from, I think it was Michael Nygaard, was about using Datomic as a testing like framework where you could take an entire, I think his example was a banking system where they could run an entire day's orders through the system.
Right.
So they could basically replay production. And then what they would do is they would then in the database, run it twice and essentially make sure that, all of the actual, the inputs and the outputs like kind of add up to resolve in zero. So, if you've got currency in, currency out, it should all be, minus the fees or
right. You should
all those kind of things.
Amount of money.
should all be, yeah. So you kind of like, you can do this thing. That's a very interesting, like global testing model, I think, because
isn't that like simulation testing? Simulant.
Yeah, that kind of thing. Yes, because simulant. Exactly. I think it is exactly simulant. Because we've talked so far about like functional testing and maybe it's a little bit of integration testing. But this like simulant, this global testing state looks very interesting. I've never done anything like that, but the concept of it looks very interesting. And we're looking at some blockchain stuff now at work, and that's something which we might want to do going forward, have a look at that to see, well, if we run 1,000 transactions on this blockchain, in theory, if we do it all again, it should all add up to the same thing, Right. Everything should be agreed and everything should be confirmed in the same way. Maybe that's not so interesting for other use cases.
No, I think I would love to do that. I've never had an opportunity to do this kind of simulation testing, but to me it's great. It's like a great idea. Like you record the result and then you just, because that's the thing, like maybe you don't even have tests yet for that result, right? You just record it and then later you can see, when did we have this problem? How far back does it go? And so you can test the past, like, oh, this is where it started. Okay, we see now.
Mia, isn't this a perfect use case for Kafka actually? Because Kafka, you just read back the events and start playing them forward as a Kafka consumer.
That is the theory, isn't it?
Well, I've done it and it works, but isn't that if it doesn't work like that, then really you need to tell us, because I'm going to stop using it tomorrow.
It does. We've had some weird issues with just trying to get our setup to scale, but it's definitely not a problem with Kafka. I'm reading about this because this is actually the first I've heard of it. So I am frantically reading blogs while you guys are talking about it.
Okay.
Do you have a use case for why you like roll it back and replay?
Yeah, actually. So if anything in your system goes down and you lose like a set of messages, The behavior with all the messages is idempotent. So if you roll back and if you replay all the messages that you lose from one system and then roll back and replay your system like the next step, then it'll get all the messages that it was supposed to have missed and it'll do the right thing. So if at any point one part of your distributed system drops out of anything and you miss some data that's supposed to go through the system and do all this other stuff,
it can just tell you where it left off, and you just
then put it right back. Yeah, like it never happened.
That's cool.
The thing with Kafka that's a bit tricky, and we're getting into Kafka, not Clojure to some extent, but so I don't want to dive too deep there, is this kind of like ordering of the consumers. If you don't do that right, then I think you can definitely have problems in replaying events. But that's a different story. Yeah.
Yeah.
Okay.
I think that
it's kind of like. Sorry, go ahead, Mia.
Oh no, you guys. Just gonna say, I think that we've run over when we usually go to the REPL, mostly because testing is very exciting. But
That's true. That's true. Let me find my thing to read.
We often got people screaming in the chat to say REPL, REPL.
Well, someone just called Clojure programmers snobs.
I mean, are you a snob if you're actually just like if the language is better?
Dang.
Why did you say that?
Oh, don't start anything.
Yeah.
I have had the experience where I just was expressing that I like Clojure, and someone was calling me a fanboy because I was expressing, I was just doing a good job saying why I liked it. Like,
I think you are a fanboy of Clojure.
Yeah.
Yeah, I guess so.
But I mean, it's the kind of like when you have a tool that's so good and it just does these great things, it's hard not to love it that much. And when you express that love, like you're a fan, but you're not a fan because it's your favorite sports team. You're a fan because it's the best tool for the job at hand and you are appreciative of it.
Yeah.
Yeah, I always think fanboys are kind of uncritical rather than like, they uncritically accept everything that Apple does or whatever. But I think we're like,
oh, Apple. Why is it Apple?
We like this. Well, that's the canonical fanboy use case, isn't it? But I mean, and I have been a fanboy of Apple. It doesn't matter. REPL. We're getting the calls in the chat.
Okay, all right.
I will say, I don't think anyone has ever. No one has ever accused the Clojure community of being uncritical.
No, exactly. Very good way to close it up there, Mia, I think, yeah.
All right, we're about to switch over to the REPL. If you're listening on the audio version, we're going to end it here. You can go to YouTube and find the video of us typing at the REPL. But right now, it's ending. And if you're still here on YouTube watching us, yay, let's go into the REPL. Let's do it right now. Let's do it. There we go.
REPL.
Boom. All right, so we have a cool exercise. Just like last time, it's from Project Euler. Also, Euler. Project
Euler.
I said Euler.
I was taught Euler, but it's actually like nobody in Germany would pronounce it that way. So anyway.
Oh no! Wait! Say it. Say how they pronounce.
They would say Euler.
Oh, that's too hard.
Euler.
No, difficult.
Not going to happen.
No.
Oh no! It's too long to paste in the chat.
The problem definition.
Yeah. Don't worry, I got it. I'll trim it into 2.
145 is a curious number. What?
So
1
curious.
factorial plus 4 plus 5.
So I'll read it. 145 is a curious number, as 1 factorial plus 4 factorial plus 5 factorial equals 1 plus 24 plus 120 equals 145. So it is a number that is if you take the factorial of all the digits and add them together, you get the same number as you started with.
Oh, okay.
Find the sum of all numbers which are equal to the sum of the factorial of their digits. And then there's a note that 1 factorial equals 1 is not a sum, so it does not count. Also, 2 factorial equals 2, so they should not be included in the sum of, the big sum that we're trying to find.
Oh, interesting. Okay.
So I went most of the time last time, so I'll leave it to someone else.
Who wants to type?
I can't do mathematics, so not me.
Well, we need a factorial function. We should be able to write that, right? Let's see. So is factorial one of those that you could mess up easily and get a bad performing one?
Yes, except we're never, like, here's the thing,
Okay.
like, we're never going to take the factorial of anything bigger than 9. So we could just memoize our crappy implementation.
Okay, I'm going to do, I think, this one. Right. Let's see.
Except, are you going to have a 0 in there?
I hadn't thought about that.
Let's see. Yeah, you have a 0. So start with 1.
Range 3 and 2. 1. Okay.
All right, is it?
You need to ink it. Ink your X to get it inclusive.
Bruce. Sorry. Is that coming out right now? Let's see. Yeah. And what was the other one? Let's see. Factorial 5. Convinced. We don't need to do generative testing on that one. So that's likely a pretty efficient one, I guess. I don't know.
Yeah, probably. Pretty good. So then what do we have to do? We have to split up the number into digits.
I felt like we did something with digits, right? Yeah.
Oh, yeah.
Was it like the rim and mod? And that was one of them. And we had, or string-based approaches too, right?
Yeah.
That just feels techy. Yeah.
I like that though.
Maybe someone else should do the digits. We could do a string one if you want.
Digits. X. We're going to take X, turn it into a string.
Yeah.
Oh, I should do double. Map stir on it. And then map integer parse int. The digits of 120.
There we go.
Yeah, even though that solution seems yucky for some reason, it's readily understandable. Like digits, as humans, we write a string of digits out. So,
exactly.
You know,
yeah,
close to.
Don't we do like? Can we do juxt, str, parse?
Juxt?
Finally get a juxt.
No.
No,
It's too early. It's too early for juxt.
Maybe you want to compose. You could put the stir and the parse int together.
Oh yeah, compose it. Yeah, that's fine. Yeah.
Okay, so we have the digits, and we need to calculate the sum of the factorial. So that's reduce plus 0 map factorial digits. What was the number? 145?
Yeah.
Whoa.
Boom.
Okay, and that's pretty fast. Okay,
Yeah.
Now what do we need to do?
It says all numbers, but that seems quite hard, you know?
Well, I mean, so you can only go up to 9 factorial, right?
Find the sum of all numbers which are equal to the sum of the factorial of their digits. There's got to be a stopping point, an obvious stopping point.
I mean, the stopping point is 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial, etc. to 9 factorial. Like, that's the end.
No, because you could have the repeated digits. You could have like.
Oh, that is the problem.
No.
Oh, do we have to do is repeated digits? Oh, shit.
I mean, so you could know at some point, like, well, the factorial is bigger than the number. So like we don't need to like.
Oh, okay.
I guess wouldn't the factorial just be 9, 9? Like, yeah, 9 factorial times 9.
Yeah, I think Mia's right. The largest factorial we'll ever compute is the one of 9.
Yep.
Of that digit.
Yep. You've got 9 digits of 9 factorial. Yeah, that's the biggest one. That's the upper bound.
Wait, so, what's the upper bound? Sorry, I wasn't.
Let me type it. My computer is really slow.
Oh.
9 of them? How many? 1, 2,
why 9?
3,
why does that?
4, 5, 6. Because after that, it's 10. So, like, after that, the digit, there's no more. Like, it could only
have 10 9s in a row.
Oof. Well, I guess you could.
There's got to be an obvious upper bound. Like,
yeah. I mean, if you can't repeat things, that's easy.
Maybe the other argument is that you just have to do what you're doing here is and just keep going forever, but you then just do a lazy sequence on it.
But you need to sum them.
Here, do you have a link to the actual problem on the website?
Yeah, it's in the Trello. Are you in there?
Yes, I am. I read the Trello. Thank you. Call back to episode 2.
All right. So
Trello shit.
So we need to know when to stop. So it's like a take while. And the take while, because you have this other problem, which is you can always add zeros. Because it's 0 oh no, because you can't, because that'll add a 1 to it. 0 factorial is 1. What happens when we do 0 factorial? Factorial, did we get that right? Okay, we got that right. Right, it's range 1, 1. Okay.
Martin says 9 factorial 7 is the upper bound. What, Martin, explain this. Explain yourself, Martin.
9.
Yeah. What is 9 factorial 7? You mean like 97? No, that can't be the upper bound. We're waiting, Martin. There's a little lag. And then he's got to type.
Oh, hello. All right. Jack is here. From the problem page. Oops.
Oh. Mm-hmm.
Oh. So they didn't expect us to get this.
9 factorial times 7, is that what that is? Is
it's a 7-digit number.
7 9s. Oh, because 9 factorial times 8 results in a 7-digit number, so that one is bigger than any possible sum.
Yeah.
Okay.
Okay. Well, that's easy.
So that's our upper bound?
Is
like that 2 million number? 2.5 million?
7, so 7 9s, whatever that is. 1, 2, 3, 4, 5, 6, 7.
No, it's 7 factorial 9, isn't it?
No, because what he's saying is
9 factorial 7. Okay.
Yeah.
So 9 times 7.
Yeah. Okay. So this is the upper bound. So we just have to do a range now.
Yep.
Range, and it said start at 3, right? And
Okay.
so then we're going to filter those.
Yeah.
Filter. Oh, we should write a function for this.
Yeah, this is...
FN curious.
Okay. Is it a curious number?
So equals X, and then I'm just going to copy paste this part.
Mm-hmm.
Let's see. Curious of 145. True.
Beautiful.
Okay, so then we're going to do, what was I doing? We had the range starting at 3 to 1, 2, 3, 4, 5, 6, 7. And we're going to oops, filter curious on that.
Wait, but don't we want the range 3 to the 2 million number?
No, because that's the
0.99
sum.
mils.
But the
But
sum
if
is
that's the upper
also
limit.
x. And that's the whole point, is the sum is also the number, right?
Right, but this is the highest number we need to test because at 9 or
Oh,
8
gotcha.
nines,
Okay. Yep, I gotcha. Okay. Yeah.
the sum is too big.
Yep.
Okay, so
Okay. Yeah.
this should work, and so I should just sum them.
So now we find out why this is a Project Euler problem, right?
Right.
That's
Here we
gonna
go.
take forever. Yeah.
There, it is taking for. Oh wait, I pressed the wrong key.
Oh, we need the sum of all the curious numbers.
We need the sum of every single
okay.
possible curious number, and now it is running, and so it is slow.
So we could memoize the factorial, right?
Yeah, I think that would help.
Because, or we could even turn it into a map of the digits.
That's what
to
memoize does. So
fair enough. Yeah.
Easier just to do it. Okay.
We're just recalculating.
Should I kill it?
Yeah, Control C it, and we can restart the REPL. And we can define a better factorial.
F factorial is memoize fnx. Oh, can't scroll back. Got to think of this again. So apply
star,
right, to range.
What do we have to go from 1 to
1 inc x? Is that right?
Yeah.
Our friend, I don't know how to say your name, Mogans suggests we try a shorter range temporarily to check performance.
That's true. To see if it actually works. Okay, we got to define curious. I'll just type it out again. Oh, we don't have digits. Oh.
Can you Control R in this REPL to get back to digits?
No. Let's hit enter and there we go. And then curious. I think Control R, and then when I type it puts it there. I do curious and then Control R. Ah, there we go. Okay. Now we're going to do reduce plus 0. Control R. Control R. There. And this, he says, a smaller one.
Yeah, take a few of those 9s away. Yeah.
145 is the only one under 1,000. Let's add another 9.
Yeah.
Oops. There aren't many curious numbers, are there? Okay, let's just filter it. Curious. Range 3. 4 9s. Maybe it's the only one.
That would be quite curious.
Yeah. 5 9s.
5 9s. Let's try it. Oh, there's one. And of course, it's memoizing now, too. Here's another thing. We could memorize curious. And then each time we run it, it should be a little faster.
Oh, yeah, that's true.
Ah, this is 6, taking a while. Oh, okay, here we go, 7. Dun, dun, dun.
Is this the last one we have to do?
Yeah.
Dun,
7
dun,
9s.
dun. Dun, dun, dun. Ooh.
A whole lot of calculations going on. Should only take like 10 times as long as the previous one, though, right?
Right. Is anything in here like super slow? We could skip parsing the int and just do that inside the memoize.
Well, could we do a smaller range? Because we know that from range 3 to 6 nines, there's only 2. So could we do from range 6 nines to 7 nines?
Oh, it finished.
Oh, that's it.
Wow, it just took a little time. All right.
All right.
So reduce plus 0 star 1. Is that the right answer?
So do we know what the right answer is?
We got to go to Project Euler and paste it in there.
That's a lot of pasting.
Do you have that set up?
I have it set up.
Okay.
Oh, but I got to read this confirmation code, this CAPTCHA. Oh, wrong CAPTCHA. Okay, hold on.
Are you a robot?
I thought I wasn't, but I saw some movies where people were unsure. Yes, that is the right problem, the right answer.
Woohoo!
Only 77,000 people have answered this before. Yay, we got it.
Go team.
All right.
We got it. I do think we could do that. We don't have to parse the digits. We can parse them inside of the memoize, and so we'll only parse each digit once. We don't have to stir them. We can just use them as a character.
I'm curious, Enclosure is equals faster than regular equals? Enclosure script it is, I think.
But Clojure script, that's borrowing the JavaScript one, isn't it?
Yeah. I don't know about Clojure.
Yeah. Alex Miller, where'd you go?
Does it work with large numbers? Because that's another question. I know that the dot equals on integer. Well, wait. There's some gotcha there where like the integer class. If you use that's what it is. If you use equals between instances of integer, it does a pointer comparison, and you might not have the same one. But sometimes you do. Like for small numbers, they're cached.
Yeah.
And so if you're using small numbers, it'll work, and then in production you get a big number and it breaks. It's one of those Java gotchas.
Even if that were faster, that probably wouldn't save much. It's probably the digits in the string parsing.
That would, We're creating a bunch of strings here.
Yeah.
And then parsing.
All right, I'm out of here. My lunch is over.
All right. See you later, Mia. Next time.
Bye, everyone.
Bye.
I think we should take that as a signal to stop.
I love how it was the only thing we had to do to make this go fast enough was memoize.
That's nice. Yeah.
The rest of it was just like the math, like figuring out when to stop.
Yeah, because it was calculating the factorial over and over again of the same numbers,
and we didn't do anything very like optimize-y, I have 2 maps in a row there. Filter on a range. I guess that's not too slow.
Yeah, we didn't drop down to like loop recur kind of stuff.
Right, or do it in like a
transducer
for loop.
Yeah.
Yeah, it's one of those things when you do break stuff up, like you break a problem up into like little bits. Often what happens is you wish the bits were back together so that you could break them up in a different way that's more optimum for solving the problem. Okay. Like
if they were macros instead, or
no, like if you made it like one big function.
Yeah.
They're all together, and so you can just move stuff around really easily. Whereas here, you'd have to if you move it, you're changing 2 functions because you're like, for instance, like moving the parse int from the one function that does the digits to the function that we memoized. You wish they hadn't been separated at all.
Yeah. I was kind of thinking of the case where like C++ templates were,
that's
yeah, like it expands out into this crap load of code, but then the optimizer can go to town on that and do like a little small program optimization on that thing. And
right. Because the compiler's not allowed to inline function calls or something.
I don't know.
Yeah. It's one of the things that JVM does. Is it'll inline function call or method calls.
Yep. Yeah, it could start doing cool things at the bytecode level.
Right. Except often it breaks your code if you're doing anything concurrent.
Yeah, but also I think to some extent, do you think you did that because of the line orientation of the REPL here? You know, that it's just more, it just feels a bit easier just to put the functions out there and then you can just edit things more straightforwardly.
Yeah, I kind of feel that like this experience of just typing into the REPL is not really the full Clojure experience, right? Normally you have an editor there and
yeah. But could you imagine solving this in Java? What would you do?
Oh, right. Yeah.
Would you like, you create a class, obviously, and then you have a main, and would you just do it all in the main? You know?
I would,
just like a big for loop.
Yeah. Yeah.
It would end up being like half a page of code, right? And you wouldn't be able to compose things together like we just did just now.
Right. Right. Although it'd probably be faster.
It would be, yeah.
Yeah, but
although the memoize wouldn't be as easy, you'd have to write your own cache or something to calculate.
You could go enterprise Java and use like EH cache or something like that.
Then you need a Maven.
Maven
that would probably be slower though. Again.
Just to do a Project Euler problem, yeah.
Yeah, because the cache has to cohere over a network, you know. It's
yeah.
I mean, it's not that hard to just build out your table of 10 elements. You know, I like doing stuff in C. I would do stuff like that, where it's like, I'll just pre-calculate all the factorials.
So one thing on this subject, though, like the Java would be faster if you wrote it. Like we're all pretty convinced of that.
Yeah,
but what you can do with Enclosure is you can easily explore different alternatives much more quickly.
That's true.
And get to a faster solution where you can't do that in a calcified language where you end up writing it out and you're not going to change it once you've written it in Java because you can't easily explore like you can here.
Right. And all of our pieces were so small and simple. Like you write one function, you're like, yep, that's it. That is how you do it.
Yeah.
And
I don't care if I'm a snob or not. That's the way.
Right. What happens in Java is it gets all smeared over. Like your sum is totally smeared across all this whole loop. Here we've separated out the sum. It's just reduce plus 0 in your list.
So I kind of wonder, like, do you end up sometimes with faster Clojure programs because of the fact that you can try and explore different alternatives? Whereas in Java, you do get faster code right away, but you're stuck with what you wrote. Yeah,
it's a good question. I mean, it's kind of like the question of like, is the garbage collector faster than what you would have written to manage your own memory?
Basically, yes.
Right. Basically, yes. Like I'm dealing with something like this in my business, actually, where I've come to the realization that so I have a website and I sell stuff on it, and I wrote my own code to organize the courses, right? And I was debating whether I should just use something off the shelf and migrate over. And the thing is, like, if you write it yourself, you think, well, I can make it exactly how I want it to be. And if I use something else, I'm going to have to compromise and deal with their limitations.
Yeah.
But that's not the actual trade-off in reality. The actual trade-off is you have the limits that you have. It's not ever ideal. It's never the way you want it to be, because there's going to be bugs, and you as a person running my own business and also the only employee of the business, like I'm never going to fix those bugs, or I'm never going to add that other feature that I want. And so the trade-off is less than ideal, but I have to do everything, and less than ideal, but someone else is doing it, and they're leveraging like volume because they're selling this same software to lots of people.
Mhm.
And I feel like it's that same thing. It's like, okay, it's buggy code to manage memory versus less optimal code, but not buggy, right? It's never like, oh, I could do it perfectly. No, you don't have time. You never have time to fix it all.
I'm a bit confused by the analogy there, to be honest. So
that you think if I could write my own memory management for just this problem and get it domain specific, like it would be so fast. Which is true in the theoretical. If you had the time to do it, you could.
Okay, I'm with you now. Yeah.
But in reality, you don't have the time to do it. And so it's always going to be inferior to what, Sun and Oracle have spent billions of dollars on to do a general purpose solution.
Yeah, I remember I was timing some stuff. I think it was in Plonk or something like that, and just JavaScript core itself getting faster, and the compiler, the stuff that gets emitted by the compiler, all that's getting faster without me changing anything.
Yeah,
and it was like an order of like 4 or 5 times faster over a period of like 2 or 3 years.
That reminds me of something that Gerald Sussman said in a talk. Someone asked him, like, isn't Scheme like too high level to do all this like numeric stuff?
Oh, okay.
And he was like, no, we just need better compilers. Like and then he talked about how he wrote this whole numerics suite that was just like a purpose-built Scheme compiler for this one problem, and it could emit really fast code.
Yeah.
And you could write, Scheme at a really high level and the way you expect it, but it would, for the numeric stuff at least, it would compile it really quickly.
Yeah, like Lisp was competing with Fortran back in the day, right? Like when you had compiling Lisp. It's all down to the compilers. There's nothing inherent in writing your code initially in Lisp that makes it slow.
Right.
Yeah, but often you want the dynamic nature, so people didn't compile it, and then it is slow.
Right.
But I think with the VM, what you're getting is like you say, a lot of investment from the underlying people, and it's kind of like, I think you get to a point where it's good enough that you're not going to bother anymore, and the big benefit of the Java and JavaScript compilers is A, someone else is investing in the infrastructure, and B, that's bringing people to the platform that you can then interoperate with. Whereas if you go your own way and you're for that one particular use case, then you might win, but overall you lose because you're on an island now.
For sure, and you're stuck developing it for the rest of eternity.
Even if that was a pleasure, you just don't get all the other benefits.
Even if you look at like what's going on in the Clojure and ClojureScript compilers, there's constantly enhancements for performance being added to like either the compiler itself or the core libraries that are in there. So the code is nowhere, like we haven't wrung all the water out of the stone yet. Like there's still more things that can be done to make all of this faster.
Right.
Yeah.
And like also, like we should be exploring higher level representations of our problems, right? Like even this, maybe like I look at Clojure and I'm like, this is really, really nice for expressing this kind of problem. But this is a math problem, right? That was, it's already been like turned into something very concise. Whereas, real world problems often are not so clear and clean. And I just wonder sometimes like whether filters and maps are what we really want to be thinking about.
Maybe we'll discuss that next week.
Yeah, that's kind of philosophical. All right, so we end it here.
Yeah,
we've gone an hour.
It's been good. Yeah.
Awesome. See you later, everybody. See you next time. Sorry we were on a different day today, but schedules.
Yep.
Cool. Bye.